Welcome back. We've been working on our binary tries. We're implementing the last method, which is adding to an internal node, and we've hit the point where we have our three different cases, and now we need to implement them. So we'll start with the situation where the last child is not full. So while it's easiest to write the logic going from top down, I'm going to implement them from bottom up here. So what would happen if the last child is not full? Well, if the last child is not full, I can just make a new child, which means that I want to, so I want to make a new internal. So, and we'll introduce some variables here. So a new internal that has new children on it. The children is going to be an array the same size as the one we're using right now. So it's thou new children is basically the same as the one we have right now, except for the fact that the last one is updated so that the last element, children.length minus 1, is changed to the result of calling add on it. Children dot last dot add of e. Let's see. E is, this is due to the bvec of E2 array sequence. I see what happened. Wait. Yeah, add. Oh, not a member. Dot last colon plus. My first problem is, okay, there. And then we have the challenge that found new children up, and I keep forgetting it is at the same level as us, so level is our first argument. Okay, there we go. That's what we can do if the last child is not full. We're just going to replace the last child with the result of calling add on the last child, and we make a whole new internal node with that updated array sequence. What if the last child is full, but the current node can grow? In that case, what we want to do, we're once again, okay, so we are going to make an internal. I won't forget to type level in here. And the new children on this one can be the children we had before plus one new one. And there's a subtle challenge to this. So val new children equals children cons plus and this should actually be, okay. This doesn't exist yet, but we can talk about what it means. So when I was drawing the picture over here, one of the things I kept pointing out is this bottom layer may or may not be leaves, right? If this one that we were working on wasn't level 1, if it was level 2 or 3 or 4, its children are internals. But if it happens to be level 1, its children are leaves. Now we could put ifs in here and do checks for that. But an alternative would be to make it so that every node type knows how to make a new sibling of itself, something that is at the same level as it. And this is very much like our is full. This is only used internally. So a protected new sibling and it takes an E, gives us back a bvec of E. So same thing that we, basically our type, whatever it is we are, we will give back a new thing of that type. And of course this makes our leaf and our internal unhappy to have this, so we need to implement them. And we have an, let's see, that's leaf. There we go. New sibling of E. I guess, okay, yep, the new sibling is going to have the more, because it takes an E in, it is going to have to do the same thing where we have an E2 type. And this is an E2, and this is an E2. Whoops. And copy, and I did not replace the one at the top. Paste, and paste. Okay, now the code compiles again. Still not happy because we have a bunch of stuff that's in comments here. And the new sibling doesn't work yet. But I do believe that if the last child is full, this would be a correct implementation. We'd take our children, we'd make a new set of them that has the additional sibling on there, and we would return an internal node of that size. Okay. What about this last situation? So this is the situation where we needed to make a new parent. So the new parent we know is an internal. And so we're going to wind up returning an internal that points to an array sequence that has this as its first child, and then a sibling for this. And it turns out that whole producing things all the way down works well with this same new sibling of E. We can call our own new sibling, because the new sibling, if implemented correctly, bvec of required int. I keep doing that, don't I? This one actually matters because it is a new parent, and so the int level actually gets a 1 added onto it. Okay, so internal level plus 1, because this is a parent for us. We are its first child, and its second child will be some new sibling for us, not for one of our children. There. Okay. Now we need to just implement those new sibling calls. So what does new sibling do? Let's see, that's the internal one. Let's start with the leaf one. So if I want a new sibling for a leaf, this is going to be a leaf, and it is just wrapped around an array sequence that has our one element inside of it. Okay, that's a fairly easy implementation there. What about for an internal? At this point, I can actually get rid of these 3 question marks because I believe we are returning something for all of those. Okay. What about for an internal node? Okay, well, your sibling is going to be another internal. It's going to be at the same level as you. And it needs to have one appropriate child inside of it. So an array sequence wrapped around one appropriate child. How would we create an appropriate child? Because here again, I don't necessarily know if my children are leaves or internals a priori. But that's what new sibling does. So I could call new sibling on children's head, new sibling on that same E. And then if my children happen to be leaves, I will get a new leaf storing the E. And if they happen to be internals, they will give me the appropriate internal as written here. Okay, and that is a fairly complete implementation. We haven't written tests for it, but in some ways that method can at least be invoked in the simple case here. Now to really test this, it turns out you need to get up to level 3. Whoop. Comparison fails on assert equals, oh wait, did I, okay, I think that is, it obtained a 6. Oh, no, that is the equals size, line 40. Oh, that's yes, because now my size is no longer 5. It's 6. Okay, first thing you have to check when your test fails is the test right. There we go. Okay, so this is passing. We can add to an internal. This isn't a really strong test yet. We would actually need to make sure we go up to at least level 2. This is still only adding at level 1, so we have not tested all of our test cases. But I leave that as an exercise for the viewer to write better tests for this. I also leave as an exercise for the viewer to make sure that you can change bits in alphabet. This should be more like a 4 or 5. The Scala vector uses 5. I generally have my students use 4 so that it lines up with hexadecimal digits. But those are things that I leave for you as the viewer to do to explore this further.